Hi everybody, this is Metha, your instructor for this video series. And I would like to personally welcome you guys back for another Lab Minutes video series, and this time it is going to be on Cisco Application Centric Infrastructure, or ACI, as we call it. ACI is a big topic, and we're definitely going to have a lot of contents on this in this video series. When I started learning ACI, there were two things that I had difficult time with, and they were the concept behind the ACI. As you will see in a little bit here, that something might look familiar to you or all of a sudden become completely foreign. And the second thing is the sheer number of new terminologies that you have to learn along with all these. So I figured let's go through the fundamental of ACI in our first video. I am going to introduce you to some terminologies that will probably be good for you to know before starting the actual configuration. And we will be covering some of the hardware and software components of the solution as well. Without further ado, let's get into our first video. The first thing that we are going to look at is the overall architecture of ACI. ACI is made up of multiple hardware components working together to form a solution. At the very core of the ACI, what we have is called a network fabric, which is the section right here, represented by the extended line, labeled fabric. The network fabric is a series of spine and leaf switches connected together in a very specific way. So spine switches are basically core switches whose main function is to route traffic between leaf switches as fast as possible, and these are the guys right here labeled as spine. So it looks very much like a traditional core switches that you might already be familiar with. Now the leaf switches, on the other hand, deals with providing network access to endpoints into the fabric, which are these guys right here. And you can see there are a number of endpoints that are connected to them, and there's no endpoint connected to the ACI spine switches. And FYI, if a leaf switch connects to an external network, just like this guy right here, labeled external network, that leaf switch is also known as border leaf. And border leaf switches can either be dedicated, which is usually preferred in a larger network, or they can be shared between the endpoints and the external network's connectivity. When it comes to cabling up your spine and leaf switches together, there are a few things to note on this diagram. If you look at these lines right here, this is exactly how you would physically connect the spines and leaves together. A leaf switch, which is this guy down here, always going to be connected to the spine or to the endpoint. While from the spine switch, they're always going to be connected to all the leaves and pretty much nothing else. Although there is an exception, which we will cover in a little bit, but for the most part, the spine would only be connected to the leaf switches. And more importantly, the spine should never be connected to another spine. As you can see, there's no line between our two spine switches here, and the same thing goes to the leaf switches as well. So no leaves should be connected directly to another leaf. Right. If you happens to violate that conditions, ACI miscabling protocol will kick in and disable the port and throw a fault at you. So once again, the lines should be only between the spines and the leaves. Right, that's representing the cabling. Once you complete the connectivity, basically what you get is what is called a fat tree or class topology, CLOS, named after its pioneer. The purpose of this is that leaves are always one hop away from another leaf, so the latency is going to be predictable. Right, if you trace these lines right here, when you hop from one leaf to another, it's always going to traverse a single spine. In a typical ACI deployment, it can start with as little as 2 spines and 2 leaves. This is assuming you take the redundancy into consideration. Obviously, if you only have 1 spine and 1 leaf, that would work as well without redundancy. The connection between the spine and leaf is recommended to be a minimum of 40 gig, right, with possibility to go all the way up to 100 gig today. And that's without using multiple connections. You can probably get away with a 10 gig, but Cisco definitely recommend against that and go with the 40 gig minimum. If you need more bandwidth, you can just keep adding the multiple links between the spine and leaves, or you can also add more spines. Right, ACI will be intelligent enough to be able to load balance the traffic when it detects multiple uplinks. So you can see that you can scale the fabric out very easily. And your only limitation is the number of ports available on the spine and leaf. And of course, for the entire deployment, Cisco has published some numbers as well as far as how many spines and leaves and access ports you can have. Now, one last note on the topology, you normally have leaf switches working in pair, especially to support VPC. And hopefully you guys are already familiar with the VPC technology that has already existed on the Nexus platform for many years now. And that's for the leaf, but for the spine, the same switch pair doesn't really apply, although you might want to try to keep them in even number if possible, right? Just to make the whole traffic load balancing a little bit more even, and you also maintain the symmetry of your topology as well. Now let's go through some of the common terminologies that you might run into when dealing with ACI. The first terminology is called fabric port, and these are all the ports and the spines and leaf that used to connect to each other. So fabric port's always going to be facing into the fabric. And these are the ports right here. Then you have an access port as opposed to fabric port. Access port are the ports located only on the leaf switches, and they're used to connect endpoints to fabric. So all of these south-facing ports right here, they are known as access ports. Connected to the access points are endpoints, and that's anything that connects to the leaf to gain access to the fabric. These can be things like server, whether bare metal, virtual machines, or even a storage. It can be a layer 4 to layer 7 device like firewall load balancer. Or it can be an external network for hosts in ACI to communicate to the outside world. And this can be either layer 2 or layer 3 connections. So these are some of the common endpoints that you will find connected to the ACI access port on the leaves. Then we have the term pod. Pod is a group of devices that make up the fabric, usually located in the same geographical locations. So in our diagrams right here, we can consider our entire fabric as one pod. Okay, so it's labeled as pod and usually assign a number to that. So it'll be port 1, 2, 3, 4, and so on. Then we have what's called an extension layer. Remember I mentioned earlier that the spine is not supposed to connect to anything else but the leaf, with some exception, and that exception is the connection to an external layer 3 device, where there's a router or switch that connects it to what's called an interpod network, or IPN. Right? IPN is a network that is used to connect multiple ACI pods together, whether they're locally or remotely. And this is part of the whole multi-pod, multi-site features of ACI, which we'll cover in the more advanced videos in this series. So connection to IPN should be the only connections that you see coming out the spines, otherwise the spines only connects to the leaf. And the last and yet probably most important component that we have not covered, but it's also shown in this diagram, is an APIC. Just this guy right here. An APIC is short for Application Policy Infrastructure Controller. APIC is the policy server that manages the entire ACI fabric from both configuration and monitoring perspective. The APIC operates under what's called a policy model. The policy model allows you to map application requirements into network representation. And this is certainly a new concept on ACI. So what you have is their spine and leaf switches are completely stateless by default, which means that when you first power them up, there would absolutely be no configuration on them. And this is very similar to if you're familiar with the UCSB series blade servers. And only when they have joined the fabric and received configuration from the APIC, they become fully operational. All of the ACI policies is defined on the APIC as a logical model, and then they get rendered to the fabric switches as a concrete model. And this just means that you translate the policies into device configuration. Once a switch has a copy of the concrete model config, the switch continues to work even when the APIC goes offline, right, which is something you would expect anyway. So the APIC is used for the configuration and monitoring, but the switch themselves do not rely on the presence of the APIC once the configs are downloaded in order to continue to operate. Right? It's just that you cannot make the config changes without one of the APIC server online. And we will definitely spend a lot of time on the APIC in this video series as we'll go through the ACI configuration, because that's where we going to perform our ACI configuration pretty much 90-95% of the time. And next we are going to talk about the hardware that you would need to build an ACI solution. Let me bring up the next slide right here. When you buy an ACI solution, there are normally three things that you buy in terms of hardware, and that is APIC, the spine, and the leaf switches. And first we are going to look at the APIC, since it is such an important component in the solution. The second generation APIC is based on the UCS C220M4, and there are two sizes, the medium and the large. The medium unit supports up to 1000 H ports, while the large version scales beyond that. You can buy them in standalone or in a cluster bundle of 3, which is the minimum cluster size required for production. And the part number are listed right here. As you can see, the M2 and the L2 are the two designate the second generation. The M is medium and the L is large. And that's when you order an individual server. If you want to buy a cluster, then that would be a different part number right here. Right? It comes with 3 servers. Although you can operate with just one APIC, you would not have any redundancy, and the GUI will keep putting up warning to remind you that. So at minimum, you're recommended to have 3 servers. If you buy one of these cluster part numbers, then you would not have any problem with that. You can also have more than 3 APIC, but anything after 3 would just be standby units, and it would not participate actively in the cluster until one of the 3 first active units fail. And keep in mind the APIC only runs on approved hardware, so you would need to buy the specific part numbers from Cisco. If you just grab one of the equivalent UCS C-Series server and try and install APIC, software on it would not work, and neither the APIC can run on the VM. Right? It must be on a physical appliance that's purchased from Cisco using one of these part numbers. In terms of connectivity, APIC needs to be connected to one of the leaf switches via a dual port 10 gig VIC. And if you look at the back of the server in this diagram right here, you see the port that has a number 2 label point to it. Those are the 10 gig VIC card, and they need to be connected to preferably a pair of leaf switches for redundancy, and that's how the fabric of switch discovery and management happens. Right? It's via the communication between the APIC and the leaf switches. APIC also comes with 2 management ports for out-of-band management, which is, I believe, is number 5 right here. They're just 1 gig copper that you connect to an out-of-band switch in your management network. And then it just comes with the standard CIMC port, and that is port number 3 right here. Number 4 is the console. Right, so in summary, minimum of 3 APIC in the cluster. 1 is okay for lab testings and staging purposes. And Cisco also said never do 2 in the cluster. And that's because when there's a split branch situation, there's no way to figure out which will stay active and which will go into standby or inactive. So 1, 3, or more. The second hardware component is the spine switches. As of today, these are the switches that can act as ACI spine. You definitely want to check on Cisco website to get the latest list of this, but this is what are supported today. You have options of modular or fixed switches. And when I say modular, that's pretty much when you buy a Nexus 9500 chassis, which is going to be one of these 3 options, the 4 slots, 8 slots, or 16 slots. And then you install line cards that support spine functionality in them. If you want the high port density, definitely goes with this 9500 right here. As you can see, you can scale all the way up to 16 slots. The recommended line cards right now is the newest 9736C FX, and that supports both 40 gig and 100 gig, just shown right here. And just FYI, every time you see the letter C in the part number, it means that it supports 100 gig, and this is true for both modular and fixed switches, which is the 9300 series. This particular line card will support both ACI and NXOS, so you can run NXOS today if you choose to do so, and then plan to convert your infrastructure to ACI later, right? If you're not ready to adopt ACI day 1. But it's still good to buy the line card that can support both. So one day, if you decide to convert them, you'll be hardware ready. Yep. So this model right here, 36 port, 100 gig. Well, of course, it will support down to 40 gig with the 100 gig QSFP28. And this line cards today can only go into the 4 and 8 slots chassis, and it's going to require at least minimum of 400 gig fabric module, and that's the FME. Just to pay attention, because I believe there's 3 different fabric modules type right now, and you need the highest one, which is the FME, in order to fully support this line card. Before the FX line card became available, you have almost equivalent of that, which is the EX version. Yeah, that number, I think it's a typo, shouldn't be there. It's just going to be 9732CEX. And of course, with the new purchase, you should be looking at to buy the FX right now instead of the EX. The EX is just pretty much the equivalent, but only with 32 port, 100 gig, and everything else remains the same, whether it's the support the chassis 4 and 8 slots, or it requires at least 4 of the fabric module FME. Now, the 9736PQ was the first line card that support ACI spine in the modular chassis, so you probably want to avoid that right now. It's just because it's an older hardware and it also has less performance, and it does not support 100 gig ports. Right? You can see it's a 36 port, 40 gig QSFP+. But if you have a 16 slot chassis, that might be the only options that you have, because that's the only line cards that support 16 slot chassis. And this guy requires to have 6 40 gig fabric module, which is the Nexus 9K original fabric module. Whatever line card you choose, just make sure to pay attention to the compatibility of the components. But usually the Cisco online ordering tool will make sure of that for you. Also, the best bet is to buy the switch bundle with all the components pre-configured. That way, you ensure the compatibility as well as you get the deepest discounts on the hardware. If, for example, right now there's a bundles out there that allows you to buy a 9504 chassis with a supervisor of your choice, and then you can add the 10 gig spine line card to that. It also comes with the cluster of APIC and, of course, proper fabric modules installed as well. If your network environment is not big enough to warrant the bigger chassis, then you also have the fixed switch form factor. And right now there are 2 models of that, as 3336PQ and then a 3364C. Again, C's designate 100 gig support right there. So you can either go with a 36 port 40 gig or 64 port or up to 64 port 40 gig 100 gig. All right, this is part of the Cisco 9300 Nexus product family. So that is for the spine. Next is the leaf switches. For the leaf switches, you have a lot more options, as you can see on this page. They are all Nexus 9300 fixed switches, as there is no 9500 line card that can be ACI leaf right now. If you are dealing with Greenfield, definitely look into the latest FX series, which is listed right here. There are 3 different models available right now under that series. FX can do pretty much everything that the EX can do, but also support MACsec and FCOE. Right, so you can definitely do more with FX as opposed to EX. EX is the predecessor. Now, if you are buying them brand new, look at buying FX instead. Again, the C in the model number implies the support for 100 gig uplinks. And again, those are for uplinks and not the access port. So uplink is basically a fabric port. These ports are dedicated for spine connections and should not be used to connect endpoints. Right, again, fabric port, not access port. Most of them can also run an XOS, so you have that future protection if you don't want to run ACI right now. There are also older generation of leaf switches listed down below, but you should avoid buying them if you can, as you will find that they lack certain features and have more limitations than the EX or the FX when you configure them. Also, if you plan to do a VPC, always buy them in pairs, as VPC requires a switch pair to have identical model. I'm not going to go through every single one of these. This is just provided to you as reference, so you can go through them. And of course, the preferable is if the FX, then the EX, and then whatever is available down here. Cisco ACI also support Fabric Extender, also known as Nexus 2K. If you're looking for that cheap 1 gig copper, ACI gives you that through the 2K FEX. Here's the list of supported FEX or FEX as of version 3.0 of ACI. Just remember that dual home FEX topology is not yet supported. So all the FEX needs to be connected straight through to the parent, which means that it will connect to only one leaf switch, whether using a single or multiple uplinks. Although with the FEX or a pair of FEX, you can configure VPC between them. And we're going to have a video dedicated on configuring FEX, and we will review the topology and configuration then. And that's for hardware components. In terms of licensing for ACI is usually pretty straightforward. All Nexus 9K that can be ACI spine or leaves are licensed by default for ACI. So if you have switches that were installed as NXOS and want to convert them to ACI, there's no additional license required. And of course, you need to buy the APIC appliance separately if you don't already have that. Alright, so for the spine and leaf switches, it doesn't matter if you bought it as ACI or NXOS, you are free to convert between the two without buying a different license. FEX, on the other hand, is a little different. FEX requires a separate ACI license, so don't forget to buy them. Right, it's actually a specific part number. If you're using FEX today for an NXOS, then of course you don't need a license for that. But if you later on want to convert that or put that as part of the ACI fabric, you would need to get a license for that, although it's just a right to use license. Next, we are going to talk about, the ACI underlay and overlay. ACI provides network visualization so that any endpoints can communicate with one another, endpoints located anywhere in the fabric, whether traffic is at layer 2 or layer 3. This essentially makes the fabric appear as one giant layer 3 switch. And with the same analogy, the core is pretty much your switch backplane, and then your leaf is your line card where your endpoints are connected to. The way that this is accomplished is by building multiple overlays over a single common network underlay. This is very similar to other network virtualization technologies like VPN that utilizes packet encapsulation. And for ACI, that protocol is VXLAN. And like I said, if you've dealt with the technology like VPN, the concept of overlay and underlay might sound familiar to you. And the reason why the VXLAN was chosen, and there are two major reasons for that. VXLAN is, first of all, an industry standard. And we all know historically, if you want to accelerate adoption, usually you would want to provide an industry standard protocol. And the second reason is VXLAN can carry both layer 2 frame and layer 3 packets over an IP network. And this is by using the UDP encapsulation. Now let's take a look at this diagram right here. Each leaf switch can act as VXLAN tunnel endpoint, that's what it's called, and in short, or acronym for that is VTAP. You will hear the term that gets referred to by people a lot as VTAP. And VTAP performs packet normalization by removing whatever extra protocol header used by the endpoint as it receives the packet from down below right here, where there's VLAN encapsulation and VGRE or even the VXLAN. Strip that off and then re-encapsulate them into a VXLAN header. Right, this is a standard VXLAN with minor modification to the packet header in order to carry extra information. VXLAN packet is then sent between the source and destination VTAP IP addresses over the fabric via the spine. So the communication between the endpoints that connects to two different leaves is going to have to go through or encapsulate inside the VTAP header, right, with the VTAP source IP going to the VTAP destination IP. And that's the outer header. Once the destination switch receives the packet, it would be able to decapsulate the VXLAN and then forward packet to its final destination. Right, at the same time, we'll be able to reapply the applicable protocol header back, so that will be accepted by the destination endpoint. And the detail of this is actually more than that, and we'll review them in the packet forwarding video later on in this video series. In order for the packets to be forwarded correctly, the underlay network needs to be created from an interworking of several protocols, and these are some of the basic protocols that Fabric uses to operate. The first one is something you probably already know, and that's LLDP. LLDP is where it all begins. LLDP is used by APIC, the spine and the leaf switches, to perform fabric discovery. So basically trying to use the LLDP hop by hop to discover each other and then form a fabric. All right, so that's the first protocol right here. The next protocol is DHCP. DHCP used by the fabric switches to obtain IP addresses, including the VTAP IP, and this is going to be coming from the APIC. So as a switch gets discovered, what it does is it sends out DHCP requests, and that DHCP request packets get forwarded along the way hop by hop, and eventually will hit APIC, and the APIC will assign the switch the VTAP address. And because the VTAP IP is the central of communication, it uses that to encapsulate the packet and communicate within the fabric. And we'll see exactly how this happens in the next video when we do the fabric discovery and provisioning. The third protocol that I have listed here is ISIS. The underlay network is basically a layer 3 routed network, and the network uses ISIS as a routing protocol to provide reachability between VTEP. It also provides ECMP, which is equal cost multipath between spines and leaves, so that the traffic is load balanced properly. There's absolutely nothing that you need to know about ISIS except for being aware of its presence. And that's for the underlay network. Now on the overlay side, ACI needs to provide reachability between endpoints, and the two main protocols that are used are, number one is called COOP, which stands for Council of Oracle Protocol, COOP. COOP is protocols the spine and leaf uses to exchange endpoint location information. So COOP is being run between the leaves and the spine. With the endpoint information being exchanged between the spine and the leaf, you can view the fabric to operate in a host-based routing. For every endpoint that a leaf detects, it will announce it to the spine. So when the endpoint on another leaf needs to talk to it, it just needs to query the spines, which is also known as a spine proxy, to be able to route to the destination. So the spine switch will have a complete view of the endpoint locations in the fabric. And that's when an endpoint needs to talk to another endpoint within the fabric. What about when the endpoint needs to talk to another endpoint outside of the fabric? Right? That's going to be through an external network, because external network is pretty much the path to the outside world. And the protocol that's being used to distribute the information of the external network into the fabric is MPBGP, and that's the second protocol that's used for the overlay. Right, so COOP is only used for host routes advertisement within the fabric. For routes learned from external network via the border leaf, a route gets redistributed and advertised to other leaves via MPBGP. So as the external route comes in, the border leaf redistributed into MPBGP, and then it gets distributed to the remaining leaves in the fabric. With MPBGP, routes from different VRF would be able to use the same BGP connections. This is very similar to MPBGP that operates in MPLS VPN, if you're familiar with that technology. Since this is going to be IBGP, as you know, IBGP requires full mesh connections. So to avoid having that, route reflector is used, and the spine is probably the most logical device to be assigned as a route reflector. So spine needs to be configured as a route reflector, and then the leaves will automatically be a route reflector client. And we would do that when we configure the fabric policy. All right, moving on to the next page. Now that you understand how the fabric operates, let's go over what you need to configure on the APIC to make all of these happen. ACI configuration is policy-driven. Instead of worrying about how to get two endpoints to communicate, you focus more on who is allowed to communicate, and you let the fabric take care of how to get the packets from point A to point B. Right, I personally call this a logical configuration. Even though ACI takes care of all the packets forwarding inside the fabric, it is still your responsibility to get the packet into the fabric. At the end of the day, endpoints do communicate the same way that they have always been, which is using VLAN tag or untagged packets. So you still need to configure access ports, whether they're a single port channel or VPC, where your endpoint connects, and make sure that those packets can enter the network using the allowed sets of VLANs. And I personally call that portion of configuration physical configuration. The reason why I split the configuration into the physical and logical is to help organize your configuration thought process. As you can see in a minute, that ACI configuration components can be very overwhelming at first. And by all means, this is not a Cisco documented methodology, but something that I came up with that works for me when I started learning ACI. So I just want to share the methodology with you, and hopefully it works for you as well. First, we are going to look at the physical configuration of the ACI. As I mentioned, the goal of physical configuration is to allow packets from endpoints to enter leaf switch access port on assigned VLAN. This process is, I would say, equivalent to setting up a switch port mode, port channel, or a VPC, and configuring a switch port trunk allow VLAN on the traditional switches. Without proper set of VLANs in place on a link, endpoint would not be able to communicate, right? Because the packets would not be allowed to enter the fabric. If you look at this diagram, these are all the components you need to configure in order to achieve this. And let's go over this. And the direction we're going to do is we're going to do bottom up. Right? Because the objects at the top level or a higher level will be referencing the object that gets created in the lower level, right, as designated by this downwards pointing arrows. Starting off at the base, which is VLAN pool. As the name suggests, this is the pool of VLAN, which are the VLANs that you want the packets to be coming from and allow into the fabric. Any VLAN you want your endpoint to use needs to be defined in a VLAN pool. And when I say VLAN pool, it's just basically a range of VLANs, and it doesn't have to be contiguous. VLAN can either be static or dynamic, so there are two types of VLAN pool, and we will see that when we create a VLAN pool in later video. Static VLAN is the VLAN that you tell the system to specifically use, while the dynamic VLAN allows the system to pick any VLAN from the pool, and you don't really care which VLAN ID the system picks for that. And the dynamic VLAN is usually used for VMM integration. We'll re-emphasize that when we get to the VMM integration video. But for the most part, I would say that 90-95% you will be dealing with static VLAN. The next layer up is domain. Domain represents how endpoints connect to the fabric. And this is completely conceptual. There are typically three types of domain you need to deal with. They're physical, the VMM, and L3 out. Although if you want to extend layer 2, you might need to deal with L2 out as well. Physical domain is probably the most common one, and these are for endpoints like bare metal servers, storage, or network devices, which is pretty much everything that is not a virtual server, okay, as far as endpoints. And they will be categorized or utilize a physical domain. VMM domain is used when you want to integrate VM controller to ACI, right, such as vCenter. ACI would be able to create a virtual switch inside a virtual host and push the port groups to it. So anything that gets to do with VMM integration, you will have to create a VMM domain. And as part of that, you have to specify how the ACI connects to the VM controllers. I always use the vCenter as an example just because it's the most popular VM controller out there. So things like IP address, username, password, and data center name will needs to be defined under that domain. And then the third domain is L3 out domain, which is exclusively used for connection to external layer 3 network. And this could be links to an external layer 3 routers or switches. All right, so those are not considered as endpoints. They are path to external network. L2 out is pretty much the same thing, but instead of providing a layer 3 connectivity, it provides layer 2 connectivity. All right, and those are categorized in its own domain. And it is recommended to create one VLAN pool per domain. As shown here, there's a one-to-one relationship between VLAN pool and every domain. And this is to distinguish types of connections and keep them separate from one another. Right, the physical L3 out and L2 outs are usually used static VLAN pool, as shown right here, static, 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 while the VMM domain uses the dynamic VLAN pool, although the static VLAN is also available if you want to have that kind of control and not let the system pick the VLAN ID. But usually, dynamic VLAN is more common for the VMM domain. With combinations of all these domains, you should pretty much cover all of the VLANs used in your ACI deployment. Now, skipping to the left-hand side, you have what's called an interface policies. Interface policies is pretty much configuration that you normally put on your switch interface configuration, things like link speed, CDP, LLDP, status, spanning tree protocol, port security, storm control, and so on is listed right here. Each policies can have this feature turned on or off or behave certain ways. So when you create interface policy, it controls how your interface will behave. From the individual interface policies, you group them together and create an interface policy group. And interface policy groups will get supplied to access interface. This is very similar to a port profile in Nexus Switch. If you're familiar with that, the idea is to define these interface policy once and then consistently apply it to multiple interfaces. This is true only on a single interface, where you can see share. So multiple single interface can share the same interface policy group if you want to, and that's a recommended practice anyway. But for the port channel and the VPC, the interface policy groups does more than just applying interface config. It also groups the interface together into a port channel. So what this means is every port channel and VPC will need to have dedicated interface policy group. So whatever interface that you assign to this interface policy group, for port channel and VPC, they will get grouped together into a port channel, which makes sense. Otherwise, the system has no idea which interface belongs to which port channel, right? And this is being done via the interface policy group. For a single interface, you can share the interface policy group all day long, right? As long as they have the same requirement with the same configuration of interface policies. So we skip one layer right here. It's called Attachable Entity Profile, or AEP. AEP is probably one of the most confusing concepts in ACI, in my opinion, at least when you start learning all these terminologies. But once you see what it does, it's actually very simple. So far, our access ports has all these policies configured, but it is still missing allow VLAN. Because later on, from the top down, we will assign the access ports to the interface policy group, but right now, with the information of interface policy, it doesn't know what VLAN is allowed. Right, and where are those VLANs defined right now? It's under the domain, because the domain is mapped to VLAN pools. So somehow we need to assign the domain to interface policy group in order to allow those VLANs to pass through those access ports. And that's exactly what AEP does. It maps the VLAN to a physical interface. And depending on what an interface is used for, whether it connects to a bare metal server, virtual server, or external routers, AEP may carry one or more domain. So you can see, just to keep things simple, you can create or have the same thing one-to-one or almost one-to-one mapping between AEP and domain. You might create a physical AEP that will be used only for the devices that needs to connect to physical domain, or a VMM AEP for a device that only needs to do the VMM integration. L3 outs the same way, L2 outs the same way. There might be an exception for a device like a UCS B series where you might have a physical domain access for your management. But since you run the VMM or VM's environment on the same chassis, which use the same uplink coming out of the FI or Fabric Interconnect uplink, you might need access to the VMM domain as well on the same device. So you might create a separate AEP for the uplinks for the coming out of the FI, right? That has both physical and VMM. Then the rest of the layers are interface profile and switch profiles. And this is how you mapped the actual physical interface on a switch and assign them to the interface policy groups. So the interface profile determines which interface number the interface policy group will be applied to. And this has absolutely no meaning until you also decide which switch the interface is on. So you need the combination of switch profile and interface profile in order to assign interface to the interface policy group. Cisco recommends that you have a one-to-one mapping between interface profile and switch profile. As you can see right here, for example, leaf 1 has interface profile, which gets mapped to a leaf 1 switch profile. And leaf 2, same way, and so on. This is for applying config to a single or port channel interface. Again, port channel means that all the switch access ports are bundled on the same switch. For example, if you want to identically configure port 1 through 3 on leaf number 1, all you need to do is mapping those 3 ports to an interface policy groups that you want under leaf number 1. And then it will get passed on to the switch profile leaf 1. Since the leaf 1 interface profile is already mapped to leaf 1 switch profile, the configuration is rolled out to the correct switch. Cisco also recommends creating additional interface profile and policies for every pair of VPC switch, just like how we have it right here, assuming that leaf 1 and 2s are acting as VPC pair and create a VPC domain. This way, if you want to create a VPC, you just need to map a VPC interface group policy to the interface that you want under the corresponding interface profile, and you're pretty much done. So you never have to touch or modify the switch profile ever once the setup at the beginning. All right, because you're only going to have only so many combinations of individual switches and then the pair of VPC switches. The only thing that you need to keep in mind when you do the VPC this way is that you must use the same interface on both switches in the VPC pair. So if you use, let's say, port number 4 on leaf number 1, you also need to use port number 4 on leaf number 2 for that VPC port channel. And that's pretty much everything that you need to complete the physical configuration. And if you think that is a lot of work just to get access ports set up and VLAN allow over them, you're not wrong. But the thing is, you usually need to do the majority of these configuration only ones, and once everything is set up, unless you add completely new sets of leaves, which will require you to create a new interface profile and switch profiles, the most you will have to do is mapping ports to interface policy groups. Or maybe creating a new interface policy groups if you want to create new port channels in VPC. So the majority of the config will be right here at this layer. Right? Everything else will be fairly static. So definitely AEP domain and VLAN pool. As long as you have all the VLANs and domains defined, and that's pretty much consistent on every ACI deployment, I would say. Right, so that will rarely change over time unless you run out of VLANs and you need to add more VLAN range to the pool. Then the majority of the configuration will be right here, right, which is turning up interfaces and port channels. Once you complete with your physical configuration, you can move on to the logical configuration. This is where we depart from the conventional network configuration to policy-based network constructs. This diagram right here shows logical configuration components, and we are going to this time work our way down from the top. Starting off with tenants. ACI is built with a multi-tenancy in mind. Tenant is a logical container of other configuration components. Tenant allows management separation. A user that is assigned to a tenant will only have access to the configuration under that tenant. And by default, ACI comes with 3 tenants, which is on this left-hand side, their common infrastructure and management. Management is dedicated to configuration to allow either in-band or out-of-band management to the fabric, and this includes the APIC and all the fabric switches. All right, so if you want to be able to remote into those components, that's all configured under the management tenant. The infrastructure tenant is dedicated to configuration of the fabric underlay itself. You rarely need to mess around with this unless under special circumstances. That's why I'm not showing the whole lot here. And then the last default tenant is common. And a common tenant is for putting resources that needs to be shared to another tenant. And this could be things like external routing. If you have a common routing that multiple tenants can share, right? Or it could be the services like DNS DHCP server or a layer 4 to layer 7 devices like firewall. So when you see common tenant, just keep in mind that's where you put all the share services in, for the most part anyway. In the later release, there's a way for you to share resources from one tenant to another, and not necessarily from the common tenant, right? But historically, the common tenant is used for that purpose. And I would say for the most part, that's still true. And that's because anything that you put under common tenants will be visible in other tenants. Other than these 3 default tenants, you can also create additional tenants, and these are pretty much either called a custom tenant or user tenants. By default, tenants are isolated and do not have access to components created under another tenant. And of course, like I said, with the common tenant being an exception. Whatever you create in common tenant, it is automatically selectable from all tenants. And of course, this is the way to make tenant talk to one another by putting additional configuration in there, but it wouldn't be as easy as putting stuff in common tenant and share them. Right underneath the tenant level, there's a VRF. And hopefully you guys are already familiar with VRF, or virtual routing forwarding. VRF in ACI does exactly the same thing as VRF you knows in Cisco routers and switches, which is to provide routing domain isolation. In the previous ACI version, VRF was also referred to as context or private network. So if you see documentations that refers to context or private network, somebody say that to you, then you know it's pretty much means a VRF. VRF needs to be assigned to a tenant, but a tenant does not really need to have a VRF. But for most part, they do. Just like traditional VRF, subnets within ACI VRF needs to be unique, right? Because VRF represents a routing domain, and within the same routing domain, you need unique subnets. While the VRF provides layer 3 forwarding domain, bridge domain, however, provides a layer 2 broadcast domain. I really need to stress that a bridge domain is not a VLAN, although it behaves like one in the sense that it's a single broadcast domain, but bridge domain can have one or more network subnets to support connected endpoints, because at the end of the day, endpoints still communicates using IP addresses, and these subnets needs to be defined somewhere, right? And that somewhere is the bridge domain. A subnet can just be a layer 2 subnet, or it can also serve as a default gateway for the endpoints. And lastly, a bridge domain has to be assigned to a VRF, which makes complete sense. So in a VRF, you can have one or more bridge domain, and inside a bridge domain, you can have one or more subnets. All right, next we have an endpoint group. If you have heard people talk about ACI before, you have heard EPG this, EPG that. So an EPG is a grouping of endpoints that have the same access requirements. The purpose of EPG is to make access control easier and more efficient. Instead of applying policies between individual endpoints, you apply it between EPGs. All right, as depicted right here, you can create what's called a contract, and I believe we'll talk about that in a little bit, to limit the access or communication between two EPGs. The next question is, how do you map endpoints into EPG? And there are actually several ways of doing that, which we will go through in this video series, but the most common way is by using VLAN tag. You will be able to create a mapping between VLAN tag to EPG at the port level, or it could be a per switch level as well, even per AEP. With that said, what I'm about to say is very important in how ACI uses VLAN, because it is very different from the VLAN that you and I used to know. I would say this is probably my biggest problem understanding ACI, so I want to make sure that I clarify it with you guys. Are you guys ready? Number one, VLAN is only locally significant. VLAN with the same ID on two different leaves, or sometimes even two different ports on the same leaves, may not provide the same access. Number two, VLAN tag is only used for classifying traffic into EPG, and that's it. Right? It does not determine how the endpoints will be able to communicate to one another. Right? The EPG does that. And that leads us to number three, which is VLAN does not dictate communication between two endpoints. Just because two endpoints send traffic on the same VLAN does not mean that they communicate to each other, as they might be mapped to two different EPGs. In short, VLAN is nothing but a tag that we use to put endpoints into EPG. So hopefully those 3 points clarifies how the VLAN's IDs are used in ACI. Now there's a few more things that you need to know about EPG. Endpoints in the same EPG can talk to one another by default, although they can be changed with something called intra-EPG isolation feature. But by default, if you put endpoint A and B in the same EPG, they can talk all day long, right, without additional configuration, full access. For endpoints in two different EPGs, however, they cannot talk to one another by default. And lastly, endpoint, or also known as application EPG, is not the only type of EPG exists in ACI. Since everything needs to be in an EPG in order to communicate inside the fabric, there are also EPG for external layer 2 and layer 3 network, and even management EPGs for accessing fabric switches. Right, so referencing the management tenants right here, you're going to be dealing with either the in-band EPG or an out-of-band EPG. Then there's a term called application profile, and this is very simple. Application profile is a collective group of EPG working together to represent a particular applications. It's just a way for you to be able to organize your EPG into a more logical container, and that's what application profile does. It doesn't really have forwarding or policies significant whatsoever to how the EPG operates. And lastly is the contract. Remember I mentioned earlier the EPG by default cannot communicate to one another, Now, to make the EPGs communicate, you need what's called a contract, and that is a very important concept. In the communication between two endpoints, one endpoint is usually trying to access service provided by another endpoint, so you need to designate one EPG as a provider and the other as a consumer EPG. The contract actually contains more than just the traffic filtering. For consumer to access the provider, you can actually perform things like QoS marking, traffic copying, and redirection to an L4, L7 device using a contract. So when somebody says contract is similar to an ACL, it's not completely true because contract does more than just that. All right, just keep that in mind. Once you have all these logical components configured to provide endpoint network access, it's just a matter of mapping the endpoint into the EPG. And as we discussed in an earlier page, under the physical configuration, an endpoint can be in a physical domain right here, which means that you manually map VLAN tag and normally an interface to an EPG it yourself. An endpoint can also be in a VMM domain, which means that the system already has the VLAN pushed out to the virtual switch, and there is no mapping you need to do, right? Because everything is done automatically by the communication between APIC, the fabric, and the VM controller. And this is where the whole dynamic VLAN comes into play. It doesn't matter which domain the endpoint is coming in from, as long as the interface to traffic is entering has all the VLANs allowed per the physical configuration that has already been done, the endpoint would get network access. And the minimum to a default gateway if you have that configured. Of course, the communication between endpoints, it depends on where or which EPGs the endpoint is placed into. And this layer right here is where the logical and the physical part of the configuration meet. And once you have completed all this, you just complete the full picture of ACI configuration. And that's pretty much the fundamental of ACI configuration that I want to cover in this video. Hopefully, the way that I have broken this down into for you helps you understand this better. The last topic that I want to cover before we close this video is ACI object model, which is our last page right here. We will go over this in more detail when we get to the programmability side of ACI. That's going to be a dedicated video for that, but at least I want to make a brief introduction because it is such an important concept of ACI and I want you to be aware of this. So you can keep this in the back of your mind when we start going through the ACI configuration. If you wonder how ACI is actually configured underneath, this is how it is done. There's a concept of Management Information Tree, or MIT, which represents the entire configuration and operation of ACI. It's not just the configuration, it actually also represents fault monitoring, statistics, and everything as well that you will see on the APIC web interface. This tree is made up of series of what's called a managed object, or MO. These objects are all the things that we have discussed, things like tenants, VRF, bridge domain, switch ports, any information that you may find on the fabric, CPUs, memories, statistics, health, stats, and things like that. So objects can be either logical or physical components. Right? Physical being the individual switch ports, line cards, power supplies. Similar to an object in an object-oriented programming, if you're familiar or have some basic object-oriented programming background, an object contains attributes. When you configure ACI, you actually either create, delete objects, or make changes to object attributes. And this is done via REST API. So REST API has become a more standard protocol that used to do a read or write on the configuration. So everything that you perform on the APIC QE gets converted to a REST API calls. To create or modify an object, you need to know where the object is located on the MIT. Every object has a unique distinguished name, or DN. And you'll see the term DN comes up again and again. And DN is made up of a concatenation of object paths starting from the root. And you just trace it down to the object that you want. And that gives you the DN. So a DN is used to identify a very specific object in the MIT. I guess the best thing to compare this to is the SNMP MIPS. Right? It's a concept that's existed for a while, and hopefully you guys are familiar with SNMP MIPS. MIP is made up of a bunch of OID, which is a long strings of digits with periods in betweens, and that's where you normally do a write or read to them using SNMP. Comparing this to the MIT, the only difference is instead of you using SNMP UDP-161, it becomes a REST API call as part of HTTPS request. And I guess the other difference is, unlike the MIPS, the MIT or MITS truly represents the entire ACI fabric in pretty much every aspect. And that's pretty much what I want to cover as far as the ACI object model. I just don't want to get into too much details of that. But just keep in mind that when we make configuration changes to the APIC in the subsequent videos, that's essentially what we're doing. We're making REST API calls to a specific objects via a DN. And that's it. That's all I have. And hopefully that was enough introduction to ACI for you guys. If there are certain concepts you didn't quite understand, you might want to go back and watch that section of the video one more time, or do more research on your own. And there are tons of information now on Cisco websites around ACI. And because these are all the key concepts that will make sure that you won't be lost when we get into the configuration of the APIC, you definitely want to understand what we have covered in this video. Right, because in the next video, we are now going to start to get into the configuration. And that wraps up our video on ACI Fundamental. You can visit our website to view an extensive list of our lab videos and sign up to get access to additional lab contents. Thank you for watching LabMinutes.com, and I'll see you guys in the next ACI configuration videos.